Hello, everybody. My name is Alex Jacobs, and today I'm going to be presenting this called LEDs are pretty dopant, which is a presentation on the determination of semiconductor bandgap energies. So just some background to start us off. So conductors and insulators are defined by their bandgap. Their bandgap is the energy difference between the valence and the conduction band, which correspond to the HOMO and LUMO respectively. And essentially by tuning this gap, semiconductors can be created, which are sort of in between a conductor and an insulator. In order to do this tuning, you can add dopant, which is a material other than the main or intrinsic material of the conductor. LEDs are a type of semiconductor which have a tuned bandgap that corresponds to a specific wavelength of light, which is what allows them to emit a specific color of light. So the purpose of this experiment is threefold. First, it was to determine the active bandgap energies of various semiconductors. This was done using an optical emission method. The second purpose was to determine the intrinsic bandgap of various semiconductors. This was done using a voltage versus temperature comparison. And finally, a dopant composition was determined. This was done using the active bandgap determined in the first step. So a couple of hypotheses for this experiment. The first one being that the intrinsic bandgap will be larger in energy than the active bandgap, as the intrinsic bandgap is designed to prevent undesired transitions, while the active bandgap is designed to promote desired transitions. The second hypothesis being larger amounts of dopant will result in smaller bandgap energies, as the intrinsic material is a porous conductor and the addition of dopant increases conductivity. So the first method was for the determination of the active bandgap. Essentially, all that was done was the wavelength of maximum absorption, of maximum emission, was measured using an ocean optics spectrometer. An example graph can be seen on the bottom right here. And essentially the energy of the photon at this wavelength of light, the maximum emission wavelength, corresponds to the active bandgap. We can see that in this diagram here, where the energy gap between the conduction and valence band within the active semiconductor region is equivalent to the energy of light being emitted, and therefore the wavelength of light being emitted. These two can be related using the equation E equals hc over lambda. The next method used was for the determination of the intrinsic bandgap of these LEDs. The intrinsic bandgap is sort of the energy difference of the non-active region of the semiconductor, seen here in the diagram. What was done was to place the semiconductor and a temperature probe in a glass test tube, and then heat this test tube in a water bath while applying a constant 100 milliamp current. While doing so, the voltage at the diode junction was measured with respect to temperature, and the resulting graph can be used to perform a linear regression analysis, which can give us the intrinsic bandgap. This can be seen on the bottom right here, where we have 1 over t plotted on the x-axis and qv over t plotted on the y-axis. This looks very similar to the graph we have here. qv over t equals EGI, or the intrinsic bandgap, times 1 over t plus c. As you can see, if we take the slope of this line, which we have done here, this slope of the line is equivalent to the intrinsic bandgap, and that is how we can find the intrinsic bandgap of different LEDs. The final section of the report is the dopant composition method. So blue and green LEDs use this gallium nitrogen intrinsic material with an indium dopant. The active bandgap can be correlated with this concentration of indium using the equation seen here. I've gone ahead and graphed this equation, and as we can see, increasing dopant or indium concentration corresponds to a decrease in the bandgap energy. On the other hand, red, orange, and yellow LEDs use a slightly different intrinsic material, which is a gallium indium phosphate intrinsic material with the addition of aluminum dopant. And as such, they have a different equation correlating their active bandgap and the amount of aluminum. As you can see here in the bottom graph, as the aluminum concentration increases, the bandgap energy actually increases, which is opposite to that of the indium dopant. This will be discussed further in the conclusion section. So the first set of results here we have is the emission spectra collected. As you can see, we collected emission spectra for each LED and obtained these following graphs. And we noted the lambda max above each spectra and the full width half max next to each spectra. This lambda max is about what you'd expect, with blue being at shorter, higher energy wavelengths, and red being at longer, lower energy wavelengths. We also notice that the yellow, orange, and red spectra are sort of clumped together on the right, whereas the blue and green are more separate on the left. This full width half max is a measurement of how wide the each spectra is, and we'll discuss this further in the conclusion section. So in this slide, you can see the results for our linear regression analysis. Here I have plotted each LED's graph of charge versus temperature. And as we can see, just like in the previous slide, we have yellow, orange, and red sort of close together, whereas blue and green are more separate. We also see that this is in units of joules, which is why they're so small, and has been converted to electron volts on the following slide. I have not shown the slopes here, but just know that the slopes of each of these lines correspond to the intrinsic band gap, which will be shown on the next slide. And finally, we have down here at the bottom a silicon diode that was measured in this experiment. And since it does not produce light, we were unable to collect an emission spectrum from it. But we were able to perform an intrinsic band gap analysis on it, which will be discussed further in the conclusion section. For now, just note that it's significantly lower than the rest of the semiconductors. So here we have the band gap and dopant composition results, just in numbers. I think the first thing to note is that the intrinsic band gap has a very low error for all of our semiconductors, which indicates that we obtained good data and were able to determine the band gap with high accuracy. Another thing to note is that the active band gap is consistently smaller than the intrinsic band gap. This will be, again, discussed further in the conclusion section. A final thing to note is that the concentration of dopant versus gallium does not have a consistent effect on the band gap energy. As we can see, with increasing amounts of indium, we see a decrease in the band gap, whereas with increasing amounts of aluminum, we see increasing band gap energies. So again, this will be discussed further in the conclusion, but important to note. Okay, so some evaluation of our hypotheses. Our first hypothesis is shown to be confirmed, as the intrinsic band gap was found to be lower in energy than the active band gap. Again, this makes sense. If we look at here on this diagram, we can see that we have an active band gap between the valence and conduction band, and an intrinsic band gap further out here. The idea is that we want conduction to occur in the active region and not to occur in the non-active region. So if we want transitions to occur in the active region and not in the intrinsic region, we would make the energy gap in the active region smaller than the intrinsic region. And that's exactly what we see. So, so it makes sense that we find the intrinsic band gap to be consistently higher than the active band gap, because that's how these semiconductors were designed. Following, our second hypothesis was that dopants would consistently decrease the band gap energy. However, we find very quickly that different dopants affect the band gap differently. As shown before, we have indium and aluminum dopants present in this experiment, and indium tends to decrease the band gap energy, while aluminum tends to increase the band gap energy. This makes sense, as we don't just want to solely decrease the band gap energy. We want to be able to tune it specifically to a certain wavelength that corresponds to a certain color of light. So by mixing different dopants, we are able to achieve a more accurate and more precise tuned band gap, which corresponds to a better color. And finally, just some conclusions. So commenting on the silicon diode, we found that it was not a semiconductor. This was calculated because we calculated the population ratio of the valence versus the conduction band electrons. And we found it to be very small, under 10%. This means that there's not enough electrons in the conduction band to allow for conduction to occur, which explains its poor conductivity. There are a few different ways to potentially increase this ratio, the first being temperature. However, it was found that temperature alone cannot increase this to the level of being a semiconductor. at the melting point of silicon, which is 1683 Kelvin, we found that the population ratio is still too small to allow for silicon to be a semiconductor. The other and more successful method would be to add dopant. Adding dopant, just like was done for the LEDs, can lower the band gap energy and allow for conduction to occur. Another question that was asked was, what happens if we reverse the direction of current flow? So as we can see in this diagram, current flows from the negative to the positive terminal through the conduction band and then down into the valence band, in doing so releasing light. Once it's in the valence band, it can then flow around to the positive terminal. If we were to reverse this flow, we would have electrons flowing from here into the valence band, and then they would be unable to promote to the conduction band spontaneously. Instead, what would need to happen is you would need to have light at the same corresponding wavelength strike the semiconductor, which would allow for allow for electrons to be promoted to the conduction band, and then flow around to the negative, what would now be the positive terminal of the energy source. So in essence, we would be, by reversing the direction of current flow, we would be turning this light emitting diode into a light detecting diode. And finally, what is the significance of the full width half max? So just to review, we see the red, orange, and yellow to have significantly lower full width half maxes than the blue and green. But what is full width half max? Half max. Full width half max essentially corresponds to the homogeneity of the system. So if we can imagine, atomic line spectrum are extremely homogeneous, as in there's basically only one state for the atom to be in the resting state, and only one excited state for it to go to. So we see a very, very narrow peak. However, with LEDs, the system is much less homogeneous. We have dopants added in potentially non-uniform distributions, leading to a larger width of transitions that can occur. And so for that reason, it can be concluded that the blue and green LEDs are less homogeneous due to their wider full width half maxes, whereas the yellow, orange, and red LEDs are likely more homogeneous due to their smaller full width half maxes. And that's my presentation. Thank you very much for listening, and goodbye.